Buongiorno a tutti, direi che possiamo iniziare. So it's a real pleasure to have Oliver Saldanha with us today. So it is also the chance for me to meet him in person because we started a collaboration with Cater Lab in 2020. And that was everything was done online, and it's a real pleasure also to have him. So I will just give you a brief introduction of him. So Oliver joined Cater Lab in 2018 and is a full-time postdoc and is a team lead of the swarm learning group. He holds a PhD in the field of decentralized AI in cancer histopathology, and the focus is the use of swarm learning to enhance molecular biomarker predictions. And so now it's time for him to give us a lecture on swarm learning for medical data analysis. So Oliver, the stage is yours.
Thank you. Thank you so much, Alessio. Yes, as Alessio already told, I'm Oliver Saldanha. So we already started, I think, our collaboration 2 years before, and we have been having a lot of Zoom calls and a lot of discussions. But now here I'm in person to discuss some of my work, our work together, and then I don't want it to be like a lecture where I'm just speaking. I just want you all to ask questions where you have any questions, or if I ask any questions, then you all can just respond. So it's like an interactive session. So welcome everyone, all the people remotely also joining. So today's discussion will be on swarm learning for medical data analysis. I've kept it very brief because medical data analysis has a lot of data types, and swarm learning is one of the technique that we are using for AI and all the other analysis that we do. So to start off, I would like to introduce our team, which is working on swarm learning in Dresden. So we are based in Dresden, Cath Lab. So the swarm learning team consists of the following members. We have software engineers, students, and also a doctor, as well as all the members of the Cath Lab are a part of swarm learning, but these people directly work with analysis and all the work and all directly communicate with all the collaborators. So this is the team. So I would be very happy to introduce you all to my team, and then I would directly start into the topic. So before I tell what is swarm learning, I would like to introduce and say what is the agenda for today's presentation. So initially, I would be telling a little bit about swarm learning, our workflow, some of the papers that we have published, what was the inspiration that we got, and then I would explain some of the interesting projects and collaborations that we have. And to wind up the whole talk, I would end up with our collaboration that we worked. How did we start and what is the present results? I try to keep it as brief and straightforward. So if you have any questions, if you have any doubts, please feel free to ask. So what is swarm learning? Swarm learning is the first decentralized privacy preserving technique. And then here the important part is the data is distributed and the privacy is protected. So only the insights of the data is shared, but not the raw data. The raw data remains in the center and only the insights gets distributed. And this technique has a lot of collaboration or potential for collaboration, as well as ease to deploy and adapt to a new technique. So this is a small introduction on what is swarm learning, but I would like to show how does swarm learning work. So what actually happens. So here you can see this is like a mock-up. So you have 5 nodes which has their own data. So what is the first step that happens in swarm learning? So there is onboarding. So say we have different centers from different parts of the world. So the first step that happens is onboarding, which is done offline, which we know which are the centers that want to collaborate and try to contribute to our model. And then you register these nodes. So all the nodes which were onboarded gets registered into a network. And after the registration, here you see these are our network. So this is very important to see that every technique or every model needs a little bit of training. So this happens locally. So here you can see there. Can you see my? Yeah. Okay. So this was our model. Then the learning happened. So these are the insights from each center. So we have 5 centers having 5 different insights. on their particular target, and then the merging happens. So this is the beauty. The data never leaves the center, but only the learning gets exchanged. So what happens? This was the first round. So in the next round, again, the learning continues from the same point, and then it merges at a different center. So here you saw the merging first happened in this center, and then the merging happened in this. So we don't know where the merging actually happens. So that's the whole beauty of swarm learning. So I should come to a point where people generally ask, then what is the difference between federated learning and swarm learning? So federated learning, it's always a centralized coordination. So the learning and exchange happens always in a central coordinator, and the learning and insights gets shared and aggregated only in one particular node. It doesn't get changed to all the centers. So there are some issues, or there are some security concerns in this. That's why we want to move to swarm learning. So you can already see one of the major concern is if the central coordinator gets attacked, then we have an issue. Then we know that the central coordinator got attacked, the whole learning gets compromised. That's why the process stops. We cannot continue the learning. That's why swarm learning is better, because if any of the node gets attacked, then that gets dropped automatically from the learning and the process continues. As well as there is another issue. So imagine a powerful contributor is the central node, and then you do your learning. And then what happens at this point is, after everyone finishes the learning, the central or the powerful node might say, if you want to use my model, which we have trained with all the data, maybe you have to pay a certain amount. So there is a very big compromise, and then the smaller nodes have to pay to use this model. So this gets eliminated in swarm learning, because at the end of the learning, the model gets distributed to all the centers automatically. So it's not kept in one particular site, it always gets distributed. And also, swarm learning is very easy to adopt, as I told, and the privacy is preserved because the data never gets shared. So coming to the inspiration. So the first swarm learning paper was from Stefani and al. From the year 2021. So they showed how swarm learning works on numeric data. So how it could be used for different analysis. They also did some COVID analysis on this data. Later on, how to show the use case of this. So this was the first paper. And then the Nature Medicine paper from my supervisor, Professor Jakob Kather, is how to detect microsatellite instability from histology slides. So these were the two interesting topics which we put together and tried to see if we could use the same concept of predicting microsatellite instability or any other biomarker, and then can we use swarm learning and make it a real-time practice. So what would be the potential results? What would be the prediction score? Will there be a drop in performance? All these were the questions that we had, which we explained with our experiments, which I will show you shortly. So now you all might be thinking, okay, then it's interesting. So what do we need? Say the center here in Milan may need to be a part in swarm learning. So what are the requirements that you'll need to have? So especially the first thing is a hardware. You need to have a local hardware depending on the application. So I wouldn't say it will need a very high GPU. If you just need to train on a small issue or maybe numeric data, or may not have big images, then you don't need a GPU. You just need a CPU or a hardware center, and then an operating system in it. And then importantly, very important, is we need an internet connection, because all the aggregation and sharing happens with the LAN connection. So internet is important, and then we connect it to VPN, and then the framework gets selected. And finally, the most important part is the data. So data can be different, but the application has to be fixed before you start training a model. At the moment, we can only use one specific data type to train our model. So if we want to do an analysis on histopathology images, all the nodes which are used in the training needs to have histopathology images and one particular problem that they want to address. So these are all the requirements which are needed for swarm learning. Then I would like to show some of our collaborators. We have some consortiums, and some industry partners who support us and with whom we work closely. NVIDIA, HPE are some of the big names, and then some of the hospitals and centers which we collaborate and make our swarm learning analysis reach wider regions. So as I already told you, deep learning or the machine learning analysis that we do is very, very data hungry. It needs a lot of data. We know that there is a lot of data all over the place, but we don't have the best model. What is the reason? We cannot share the medical data because it's patient data. We cannot share it. So this is a place where swarm learning comes into picture. Here you can see the private data always remains in the center. Only the insights get shared. And this is also the sharing of the weights and biases or the insights. It's very secure. It's all encrypted. So even when it is shared between different centers, it is well protected. So this is the surety that we give to all the contributing nodes and how they can be a part of swarm learning. So this is the background. And then here you can see any workflow. First step would be to collect the data, then the pre-process it, then the feature extraction. So all these steps could be done locally on site without having any influence of swarm learning. So swarm learning really comes into picture after the features are extracted to the prediction. So the training actually happens during the point where the swarm learning comes into picture. So we have to adapt the workflow a little bit to make it compatible and friendly for swarm learning. So at the final stage, you can see the swarm learning adoption happens. So now we come to the inaugural paper. This was the first paper that we had. We had a histology workflow and the swarm learning. We put both the concepts together. And this is the first inaugural paper from our team with swarm learning in decentralized artificial intelligence for cancer histology. We tried to predict microsatellite instability as well as BRAF. So some of the interesting questions which were answered are here. So as I told, the models that we train are always data hungry. In this graph, you can see on the x-axis, we increase the number of patients. So number of patients on each site were increased from 25, 50 up to 400. Then finally, we have all the patients. So you can see there is a standard increase in the performance when we increase the number of patients, as well as very interesting point to see here is this. Yeah. So very interesting point to see here is the merged performance. That is, when you put all the centers data in a single location, the performance of that is on par with the swarm learning. So the swarm learning performance never dropped. So it's always in par with the merged performance. So this gave us a surety that we could use swarm learning for histopathology analysis or, for instance, any kind of medical image analysis. So this is something that we showed in our paper, which caught a lot of attention. And from there, we also, my supervisor wrote some grants from which we started a lot of consortium projects. And one of the important project is Odelia, which has around 8 institutes all over Europe. And what we try to do here is try to predict tumor in breast cancer. So this is a completely different modality and a different problem that we want to address. But important thing to see here is the baseline is the same. We use swarm learning and no center shares their data. So this is what we wanted to show. And a small overview of what we do in our workflow here is the patients have a MRI scan, and then this is pre-processed and given to a model. So this is a weakly supervised technique. Why I say weakly supervised technique is we don't do any annotations on the tumor. We directly give the whole MRI to the model and try to predict whether there is tumor, yes or no. So, and then these techniques can be different for MRI because this MRI data is 3D. So we could have 3D analysis, 2D analysis, as well as multiple instance learning. We tried all different techniques and saw what's the performance. So an overview on the study is here you can see there are 3 centers which are from different parts. One is on the top is from the Cambridge. Then there was Duke data from the US, as well as there was some data from Switzerland. So no one shared their data. You can see the numbers also of the data sets are different. But then a model was trained, which was validated again on 2 different independent data sets. That was from Germany as well as from Athens, which is a center in Athens. So 5 different countries involved in the whole process, and then you can see how was the performance that we have. So the first step that we did to finalize which is the technique that we have to use and what are the hyperparameters that we need to fix is on the A panel of the figure, you can see we have different techniques in the x-axis and how do they perform. And on the first panel, what we did is we split the whole open source Duke dataset, which was available into 4 parts. The 3 parts were used for swarm learning, and the final part was used for validation. So this is called the internal validation that we had used. And in the second figure, you can see the same concept, but we didn't use the internal validation, but we use the external validation, which is validated the same models on the Archon data set. So here also one interesting thing we observed is the swarm learning models was in par with the merged model as well as the ResNet 101 3D model, which we used, performed the best. So the next step would be how do we use the same analysis in the real world scenario? Here you can see 2 more results where on the x-axis you have different centers performance. So the best performance you had was around 0.75 on one of the center, which is Duke. And then when we use swarm learning, we got a performance which was around 0.8, which outperformed all the local models. So this is on the Archon data set, and the performance even improved when we went to the Athens data set. So this shows that the models that we generate are more generalizable and also have a very good insights on different kind of data. So when you give a new center or data from new center, it always performs better than the local model. So this is what we wanted to show. And another consortium or another project that we are working on is histopathology analysis for risk prediction and also for survival analysis on histology images. So here we have 5 centers across Germany, and here we try to predict different outcomes like survival, what is the prediction of, or maybe sometimes response prediction also. But here we use histology data and try to predict these interesting biomarkers without sharing actually the data. And the final, before the final, we have one more consortium project, which is SWAG. Here we do generative AI. So generative AI is generating images, synthetic images for either you can use it for training a model or making it better, or also for educational purposes. So sometimes you cannot show actual patient data for educational purposes, so you need to generate some images. So even to generate an image, you need to train a model which generates these images. So this process is also done with swarm learning, which is adapting the technique to a different application. So this is done with SWAG. And then we also have a nice project on surgery swarm. This is the real-time analysis or use case of the project that we are doing. Here we try to predict, this is a prototype study, but actually we have put systems in hospitals and no one shares the data. So we want to predict the inflation in appendicitis, how inflated it is, but this is just a prototype application because it's very evident in the image when we see or in the video when we see. But what we want to do is go towards cancer detection, try to see whether from videos we could directly predict whether there is cancer or whether there is a reoccurrence of cancer. So that's the interesting thing that we want to do. Here there are 6 centers which are participating in the study, and we have some nice results which will be published soon. So, and now coming to the very important part, that is the analysis or the work we did with Alessio in the center. So this didn't involve any swarm learning because all the different centers data was collected and aggregated. So that's why we didn't involve swarm learning, but I think that would be a potential use case. So we have different centers in Europe that you can see here and their numbers. And here in the first panel, we clearly see we wanted to predict PBC AIH from the liver histology image that we got. we tiled the whole slide image and then fed it into a transformer to extract features. And these features were given to a multiple instance learning workflow. And then we wanted to predict whether the whole side image or the patient is PVC or AI. So when we did internal cross validation, we had a very good performance, which motivated us to have an external cohort. And when we did external validation also, we had a performance of 0.81, which was very good. And we have written our manuscript and submitted it for, yeah, it's under revision at the moment. So some of the visualization, these were 2 patients which were correctly predicted and 2 patients which were wrongly predicted by our analysis. So you can see some heat maps and some visualization on which were the interesting parts for the model. And that's my time. I think I am, yeah, kind of within time. Thank you so much for this wonderful opportunity. Please, if you have any questions, feel free to ask.
Thank you, Oliver, for this wonderful presentation. And I think you were really convincing that swarm learning is the way forward. And so what are the practical steps for a center to move toward a swarm learning field?
Yes, very, very good question. I think the practical step would be to identify which is the data type that we are using for the analysis and a very interesting endpoint. So endpoint detection also plays a very important role. So what is the endpoint that we want to predict with our model? And does all the centers which are contributing have the same kind of data and have the ground truth that is the endpoint for prediction? So these are the initial steps or initial discussions that we do. Then we go forward seeing what is the pre-processing steps that has to workflow and which is the technique that we need to use for this. So these are the standard steps. And then once all these initial discussions are finished, then we go for the infrastructure, whether the center is able to share the weights and biases. Some centers have firewall, which give us a little bit of hard time to set up, but these are all the practical steps that we go forward. And once all the setup and pre-processing technique, everything is finalized, then we go forward and start the swarm learning technique. So yeah.
Well, thank you for your presentation. I would ask a question.
Mm.
Could you do that? Could you do that an example of what pre-processing really is for? I don't know, one of the project you presented us today.
Yes. So pre-processing, I can also take the histology example because the whole slide images that we get from different centers might look completely different, right? So it's very important that we normalize these images. So all the images look in a similar format with a similar color. So that's why we normalize all the images based on one particular image, which is like the comparison for us. So this is the pre-processing. What happens is the whole slide images get styled into smaller patches because the present hardware that we have cannot process a whole slide image because it's 100,000 cross 100,000 pixels. So that's why we try to do it in smaller patches, and all the patches are normalized. So this is the pre-processing, basically tiling it, normalizing it, and then it's ready for feature extraction and then analysis.
Coming back to the practicalities, so in the projects that you showed us, like Odilia, right, the centers involved have already, of course, an infrastructure for swarm learning. That means that they have also people like a bioinformatician or computer scientist dedicated, I mean, not to the project, but in the department. Can you add up on that a little bit?
Yes, I think whenever we start any project, one of the important requirement will also be a person in contact. So each center will have a person in contact with whom our swarm learning team can directly coordinate or communicate. So this person in contact can be either a clinician who is doing his master, like his doctoral thesis, or also a employee who is involved in the IT. We need to, this person needs to have a little bit of IT background so that we could ask him to connect remotely and then do some analysis for us. But basically, any person who has some background on IT infrastructure, this person will be the person in contact who would help us set up the infrastructure for them. We don't need to go in person, everything happens remotely, but we need someone who we can speak and set up a call so that we could process this. Yeah, I think there's a question.
So, first of all, thank you very much for your presentation and for the brilliant idea that is behind your presentation. I'm a statistician and old generation statistician, so my first question is, and it's a curiosity. You showed us only the performances of your models, let's say, but what about interpretability and explainability that are behind your results?
Yes, very, very good question. Thank you. Yeah, interpretability and explainability, we try to have heat maps is one of the very important aspect of the visualization or interpretability. So what we want to do is we want to focus on the region which the model focuses on and gives this prediction. So this region is focused, highlighted, and then showed to a pathologist who can give us, okay, why is the model looking at this region? It is not only done for the correctly predicted ones, but also the wrongly predicted cases, so that we know, okay, this is the region where the model is going wrong and what can be the potential reasons. So a lot of times it so happens that when you train any deep learning model, the model has not seen enough cases to understand what is going on. So that's the issue. Or sometimes it can be a very big artifact which can be there on the whole slide image, which can lead to a wrong prediction. So what we see is which are the regions which are interesting or which are rated pretty high or the model has given higher attention to. And then we try to speak with the pathologist and ask them, okay, tell us why is the model going wrong here? So this is one of the major, either a heat map or a visualization technique of that sort. Yeah.
Hi, thank you very much. It was very interesting due to the opportunity to avoid sharing data, but we need a different amount of data in each center. I saw different sample sizes in each center. How do you consider this in terms of different contribution to the model, to the training model, and the imbalance that this may generate? And linked to this, how does the merge work in the model? Thank you.
Very good question. Thank you. So what happens in actual, okay, I'll answer the second question first. So merge is nothing but aggregation. So if there are 5 centers, the learning is different weights and biases. The model in architecture remains the same. So what happens is at the merge step, all the weights and biases are sent to one center and they are all added up and divided by the number of centers. So it's just aggregation, but this could be changed. We can also do some different kind of techniques, but the present analysis or the results that we have is basically aggregating all the weights and biases. So this is the aggregation technique. And also you asked a very interesting question of what happens when there is an imbalance. So what we try to do is we try to end the training at the same point. So how do we do it is the centers which have more data are trained for lower number of epochs. Center which has less data are trained for more epochs, but then the weightage given to that model or the center is lower. So somehow it balances out with the weightage and the number of epochs. So if one center has 50% of data, then it is trained for 2 times more epochs, but each epoch contributes to half of its weightage for the model contribution. So that's when it balances out. And yeah, this is how we take care of the imbalance in the different centers. So at the end, when we see the model that all the centers receive have the same weights and biases, so it performs the same when we validate this on on an external cohort. Yeah, thank you.
Coming back to the ethical regulations. So it seems that swarm learning can be quite helpful because it overcomes the problems of data sharing agreements and so on. Is that true in the reality? I mean, in the projects that have been EU funded, I mean, from a bureaucratic point of view, did you have any issue in terms of really deploying the project in the real life?
Yes. What we have experienced is, to be sure, we also do a data sharing agreements with all these studies. So for Rodelia, we also had a data sharing agreement with all the centers, but there is a white paper that we are working on, and also HPE has put out, which shows that if you use swarm learning, you don't need to have a data sharing agreements, but we don't have any conclusive guidelines on this aspect, since the field is moving pretty fast. So we are still waiting for, but to be on the safer side, we also do some data sharing agreements, even though we don't actually share the data. But for these projects which we have, we do a data sharing agreement. But potentially, once we have a white paper out which says that if you use swarm learning or federated learning, you don't need to do any kind of, which is in regulatory terms accepted, then we don't need to do anything. But now still, I think it's a topic for discussion, which is still not approved. That's why we try to be on the safer side and do a data sharing agreement. Yeah.
Thank you for your presentation, for bringing a little bit of digital pathology in this afternoon. 3 questions, but short, I promise. Relinking to what Alessio was saying of the complexity of having, the necessity of having an IT service or someone with a background in computer science in the center that has to participate, right? Are you thinking of simplifying this kind of thing, like giving easy to use instruments to extract the features from the images? Because this would, of course, expand a little bit the cohort of people that can participate. I'm thinking about pathology departments without a computer scientist inside that can provide some new information. The second is on normalization. If you normalize all the slides from all the centers that are participating, the final algorithm will perform really great on a normalized new cohort, hopefully. But in this case, you are losing the benefits of heterogeneity of the images from the other centers. So how do you are thinking of progressing? You are planning to continue normalizing or accepting the challenge of not normalizing anymore to apply this on highly heterogeneous real life cohort? And the last one is how do you are dealing with the ground truth? I saw the MRI images that are weekly supervised, so just labeled tumor, non-tumor. I imagine that those labels are given by radiologists. Are you trusting a one-shot diagnosis from one radiologist? And what's your perception about the liability of these ground truths that we are using?
Thank you. Okay, let me try to remember what was the first question. So I think the first question is, can we make this workflow simple? Definitely. What we have done at this point is we have a very step-by-step instruction. So we don't need a computer scientist on site, but somehow who can run a script on Linux or something. So we have made it as simple as it could get, but definitely there is some room for improvement. So now we don't want someone to debug issues. So all the pre-processing is just running one shell script. So run pre-processing, so it does all the pre-processing for us. So setting up, onboarding a swarm learning, just run swarm with the IP address or something. So you have some placeholders where you have to mention the IP address of the center, and then it does everything. So you don't need to go through the whole script or clearly understand. So we have tried to automate the whole process as much as possible and adapt it for a specific projects. But still, we are trying to make it better with time, but we have come a long way, I would say. If I see the time we started in 2021, it was all manual. Someone had to start from all 3 centers at the same time, but now everything can be automated. So they have to just run a command and everything starts. So this is how far we have got, but still there can be some room for improvement, which we are constantly working on. The second question was it on the ground truth? Okay, normalization. What we see, a very interesting question. What we see now is there is the self-supervised learning, new models which are transformer based, which extract features. For this, even if you give the unnormalized data, the performance doesn't drop, because the different centers having different variability, it helps the model, and the features which are important are picked up by the transformer model. So after, if you do a normalization or you don't do a normalization, the performance drop is not that massive. So we can just, in the future, what we see is we can just leave out normalization, and that would not bring down any particular performance drop that we have. And finally, in the Odelia project, the ground truth that we used was all biopsy confirmed. So somehow histology confirmed also. So it was not only the radiologist telling us whether there is tumor, yes or no, but also we have, like, the sample was sent to the pathology and then confirmed that there was tumor, which was malignant or benign, depending on what it is. So this is what we are doing at this moment. I think in the future, I don't know where the exact ground truth, because now we are in an era of large language models, which could also take a radiologist report and give us what is the ground truth, whether there was tumor, what was the dimension of it, and then this could be used to train a model. But we are still figuring this out, what can be a very good ground truth standard that we can use. But at the moment, we are only using the biopsy confirmed or the histology confirmed results or ground truth for our analysis.
So I want to ask another question. This is more like something of personal curiosity more than anything. But what do you think about this rapid evolution that this new branch of science has recently, got into? And what did pathologists, anatomopathologists, and radiologists thought about this new, I would say, application of machine learning? Is this a valid instrument, or that is an addition to other things pathologists and radiologists have, or is this gonna be like a substitute for their work? I want to know, what do you think about this now, and what do you think the future might have for us to uncover about these new technologies? Thank you.
I think it's a very interesting question, but somehow what we have worked through, as you told, this field is evolving so fast, getting better and better with time. We never intend to replace pathologists, because what we always try to do is reduce the work and guide them in a channel. So somehow this is all that we can never eliminate either a radiologist or a pathologist in any ways, because the amount of insights that they can get into, we are still not in that state, or in the future. What we can do is support them and reduce their workflow. So like working hours, or try to ease the decision making. So this is all that we are trying to work towards. And I think the field is also moving in that direction to assist and not replace. So this is what we are very keen on working, is to how we can help the pathologists as well as the radiologists to in making decisions, and maybe try to get some more insights which only from the images a human cannot detect. So these insights are something that we are trying to find out, which will not affect any way the pathologist. But the response from the pathologists and radiologists is also mixed. Some of them are very positive about what we are doing and try to help, and some of them are a little bit suspicious. But I think all the pathologists who have collaborated with us have a good feeling, because they know the insights that we want to get from this whole slide images is not to kind of replace them, but to help them or give more insights on what is present in a whole slide images. And I think this field of cancer or oncology has a lot to be discovered, and then we are moving in the direction to discover new things. So hope it has answered your question.
Okay, so it was an excellent discussion. Thank you, Oliver, for being with us.
Thank you.
Thank you all for the coming.
Thank you.
And that's all we really.
Questo è un po', cavolo, mi serve di nuovo che qualcuno rimette via le credenziali, perché sennò non posso rimettere il microfono.
Salve qua,
No,
è costato.
ma come lo... lo posso fare?
È stata veloce.
Nel
Per
frattempo
una volta.
chiudiamo qua. Come la penso?
Oh, è così, eh.